Hey everybody, welcome back to another lecture video. In this chapter, we're going to be looking at actually the last of the organic chemistry chapters, and we'll be transitioning, starting chapter 20, into the biochem chapters. So this will round out the organic molecules and concepts that we need to start looking at, like I said, the biochemistry. So we're going to look at carboxylic acids, anhydrides, which are derivatives of carboxylic acids. So we're going to look at carboxylic anhydrides, esters, and amides. All of these are born from carboxylic acids, if you will. So we're going to look at how these are different. So in this chapter, as I mentioned, or actually in the last chapter, we looked at carboxylic acids. So in this chapter, we are going to see that each of these is basically related to the anhydrides, the esters, and the amides are related to the carboxyl group losing an H2O. So in our carboxylic acid, we're going to lose an H2O. That would be including an H that's going to come from a neighboring molecule. So reactions with carboxylic acids that produce either esters or amides or anhydrides have to have some kind of other OH on them somewhere. Other hydrogen coming from somewhere so that we can get that water molecule. Now, in all of these, we're going to see that the carboxylic acid reacts with something. In the anhydride, it's just two carboxylic acids together. So in this first example here, here's carboxylic acid 1, and this is carboxylic acid 2, drawn slightly different. Notice that they are exactly the same. These are both, whatever this R group is, we could just say that's an H and make this formic acid, have it just be the simplest. This could also be formic acid, or it could be something different. But they both have that carbonyl, the C double bond O, and they both have an OH attached to that C double bond O. Now the reason it's not shown the same on both sides is because one of these is going to keep its O while the other is going to lose its O, but that's what forms the water molecule here. So in the anhydride, it's just made from two carboxylic acids, and the word anhydride almost sort of means without water. We call things anhydrous salts when they're missing their water. And we call them hydrates when they do have their water. We won't go into that. The carboxylic acid reacting with an alcohol is going to produce an ester. Okay, so remember, an alcohol is an O attached to some carbons that has an H on it. So a hydroxyl group, basically on one of our alkanes, would be an alcohol. Now, primary and secondary alcohols, I believe, are going to be, no, maybe tertiary alcohols can react too. Nope, primary and secondary alcohols. There has to be, no, I think a tertiary will act. Sorry, I'm overthinking it. I'm thinking of some of our other reactions or oxidations. Any alcohol should be able to do this. And then with the last group, the amides, instead of it being an alcohol or a carboxylic acid, it's an amine. So a nitrogen-containing compound. Now this is just ammonia, the simplest amine, or the simplest nitrogen-containing compound. But an organic compound would be an amine. So amines yield amides, alcohols will yield esters, and two carboxylic acids together will yield an anhydride. So the functional group of an anhydride is two carbonyl groups bonded to the same oxygen. Okay. The anhydride may be symmetrical, like here, or it can be two different groups. To name the anhydride, we basically just drop the word acid from the name of the carboxylic acid from which the anhydride is derived. So since these are made up of acetic acids, we would just say this is acetic anhydride. We're not going to worry about naming anything more complicated. If you had a carboxylic acid that was unsymmetrical, something like this, you could just take the long end. This would be 1, 2, 3, 4, so butanoic acid, and we would say butanoic anhydride. Of course, this would probably be butanoic anhydride. We're not gonna, I don't even know how to name an anhydride that has an unsymmetrical side. That's not something that's typical that you learn how to name, so don't worry about it. But that's where these names come from. If you were to hear acetic anhydride or formic anhydride, you could then sort of kind of picture it. The esters, again, the functional group of an ester is the carbonyl group, this time bonded to an OR group, where the R could be alkyl or aryl, meaning it could be a benzene type ring, or it could just be a regular CHs. You can see that here. Now this one has two of those ester groups on them. The O8 is how we name esters. You can see the name there, and I'll go over that in a second. So when we're naming esters, there's IUPAC names and there's common names. Both of them come from the parent name of the carboxylic acid. So in this case, we have ethanoic acid, and that's actually another thing that you should be able to do, is look at an ester and figure out which part is the carboxylic acid part and which part is the alcohol part, because that's important for naming. It's easy. You just draw a line through the O. Right. This is where the two molecules connected together, and it doesn't really matter where you put the water back in. You can put the OH and the H. Doesn't really matter, but both sides are going to have an OH on them when you're done. Okay, and so then the side that has the carbonyl on it is obviously the carboxylic acid side. So that would be ethanoic acid with ethanol. That's how you would call this group right here when you put the OH back on. Be ethanol. So the name ethyl ethanoate comes from the fact that there's an ethyl group stuck on an ethanoic acid, but the ethanoic acid, right? It's not an ethanoic acid anymore. We say ethanoate. Ethanoate, the name there indicates that it's the ester. Let's look at another one. So this is diethyl pentane dioate. So it's diethyl because this molecule, I'll show you what it looked like. It looked like this when it was the pentane dioic acid, and then there was two ethyls that came in, and so then you lose the water. We connect everything together, and we're left with diethyl pentane dioate instead of pentane dioic acid. Okay, we don't name very many di and trioic acid or dioic acids, anyways, but they are. I mean, they're very prevalent. We look at really simple molecules when we look at examples, but most molecules are not simple examples. And here we have a 5-membered ring of an ester, and cyclic esters are called lactones. And we don't have to worry about the naming of these different lactones. Okay, functional group of an amide. Again, carbonyl group, this time bonded to a nitrogen atom. Now, to name an amide, we drop the suffix oic acid from whatever the IUPAC name was, and then, or ic acid if it was a common name, because we can start with both common names or IUPAC names. Oic acid or ic acid gets dropped, and we add amide. So this guy right here was acetic acid before we stuck in the NH2, right? This is the water that left. And so acetic acid becomes acetamide. Here's a methyl acetamide. So let's see, why is that called? Oh, that's N-methyl. So here whenever there's a group on the nitrogen. So this one is still acetamide because it was from acetic acid, but this one has a group on the nitrogen. So N-methyl acetamide. This one here has two groups on the nitrogens, and it's formic acid. So this is NN-dimethyl formamide. So this is 1, 2, 3, 4, 5, 6 carbons long. So the acid would have been hexanoic acid, but it's an amide, so it's hexanamide. Hexanoic acid, hexanamide. Okay. Now, cyclic amides, unlike the lactones that we called esters, cyclic amides are called lactams. And I'm showing you here a 4-membered lactam. I'll call it a beta-lactam. There's a 7-membered lactam. Again, it's a cyclic amide. So a closed ring, we still have the same functional group, C double bond O attached to an N. I actually can't tell you why this is called a beta-lactam. It must have, this must be a 4-membered ring. So 4-membered rings are beta-lactams. Yeah, that makes sense. You can see another one here pointing to that 4-membered ring. Penicillins differ in the group bonded to the carbonyl group. The penicillins are referred to as beta-lactam antibiotics. The differences in the different penicillins, because there's not like penicillin, there's different penicillins, different strains of that, whatever it is. What is it, a fungus? Anyways, or a mold. Penicillin's a mold, I think. The different strains, right, produce different antibiotics. And so what's different about them is what's shown here in red. So the actual carboxylic acid that this amide gets made from is what varies in the different penicillins. But what is similar in all of them is that they contain that beta-lactam ring. Anyways, this one's shown as amoxicillin. I think this is a cephalosporin. These are also beta-lactam antibiotics. So this is not I'm sorry, I was going to say neosporin. This is not penicillin. This is cephalosporin, Keflex. It's another beta-lactam antibiotic here because it contains beta-lactam ring. Just for comparison purposes, notice that the group bonded to the 6-membered carbon ring here is also different. So here we've got carboxylic acid functional group and a methyl group. And over here we've got the carboxylic acid group, the methyl group. We're missing the double bond that's there, and this group's not there. And it's also a 6-membered ring where this is a 5-membered ring. So there is a difference, on this side of it as well. But the cephalosporin groups also differ with what's here, everything else staying constant. So this end of it is why it's different from the penicillin antibiotics. In any case, they both contain those beta-lactam rings, so they're referred to as beta-lactam antibiotics. How do we make esters? So esters actually come from one of the more well-known and common methods, and it's called Fischer esterification. So this Fischer esterification method, a carboxylic acid is reacted with an alcohol in the presence of a catalyst to produce the ester. So let's say carboxylic acid plus, what did I say, alcohol? H2SO4 is a good concentrated acid for this. Now, there is a equilibrium that establishes here. We would get the ester and water. And this is one of those good reactions that we can actually drive forward with Le Chatelier's principle a few different ways. We could use excess of whatever reagent here is cheaper to keep driving this in the forward direction. We could also remove water from the mixture as it forms to continue to drive this forward. If you let the water build up, then that starts to hydrolyze your ester back into carboxylic acids and alcohols. As for amides, we can kind of do the same thing. In principle, we can form an amide by treating a carboxylic acid with an amine. Again, removing the OH from the acid, the H from the amine to form a water and your amide. Now, in practice, what occurs if the two are mixed is an acid-base reaction to form an ammonium salt. So, that's what we want to happen. We want this to form an amide, but what actually happens when we mix these two is that they do acid-base chemistry. The acid, right, has the OH here. The ethanamine has a lone pair. It can form a base. It's going to pull that hydrogen off, leaving the negative charge and the positive charge, and we get an ammonium salt. Now, if we heat this salt to a high enough temperature, then water gets eliminated and the amide forms. It's much more common, however, to prepare amides just by treating an amine with an anhydride, because again, the anhydride, actually I'll show you the reaction. The anhydride is not going to have that H, and so we aren't going to immediately just have acid-base chemistry happen. So here's the anhydride. So this way, this nitrogen here, sort of like our carbonyl attack, electron seeking area here. What do we call it? A nucleophilic attack by the nitrogen on this carbon. The carbon there is a good electrophile. Wants those electrons that nitrogen has and forms a new bond. So that works a lot better than using the carboxylic acids. Now, hydrolysis of anhydrides and esters and amides we'll look at. Hydrolysis is when we can chemically decompose these compounds just by adding water. So, or the elements of water, right? Hydrogen and oxygen, or hydrogen and a hydroxide. Just say it like that, because this is actually what we're sticking back in there. Carboxylic anhydrides, particularly the low molecular weight ones, these react readily with water, and they hydrolyze to give two carboxylic acids. So again, draw a line in the middle. One side's going to get an OH, one side's going to get an H. Whichever side you decide to leave this O with, obviously gets the H. The other side gets the OH. And so we'll end up with two acids again. So you should practice this. You should find some anhydrides in the back of the book, whatever they look like. Or whatever, and then split them up, add OHs to both sides, or, HO, and draw back your acids, get back your acids. That's hydrolysis of anhydrides. Now, there are esters as well. Esters hydrolyze only very slowly. Even in boiling water, these things go really slow. Hydrolysis becomes considerably more rapid if the ester is heated in an aqueous acid or base. So water on its own, slow. Adding some kind of acid or base, catalyst, makes it go faster. And that just helps with preparing those compounds to be a little more receptive for the reverse reaction. The hydrolysis of esters in aqueous acid is just the reverse of the Fischer esterification. And actually a large excess of water will actually drive the equilibrium all the way to the reactant, or to the product side. This is a backwards reaction of what I was showing you earlier. So just here we can say lots and lots of water makes this really go this way. But again, you got to have some hot aqueous acid. Now we can also do it in hot aqueous base. I think I thought I was showing you a picture here of hot aqueous base, but I guess this isn't. This is like the same. I think that's just the same one. Fantastic. Here, let's make it like that. Hot aqueous base. Okay, that's going to leave us actually with something a little different. We're not going to end up with that. We're going to end up with this guy. Acetic, what do we call this? This will be our ethanoate ion. Our ethanoate ion, using IUPAC name. This is ethanoic acid, so ethanoate ion. That's what will happen if we use aqueous base, something like NaOH, hot base. We actually call this process saponification. When we hydrolyze esters, saponification comes from a word that meant making soap. And we actually do this when we make soap. We use hot base. Sodium or potassium hydroxides are usually the ones of choice. And we tend to do this to long-chain fatty acids or long-chain fatty esters that have really long hydrocarbon tails. So where this only has 2 carbons on it, imagine one more like an 18 carbon, I don't know if that's 18 carbons, but some kind of, what am I trying to draw here? Oh. Anyways, this is a glycerol molecule. And triglycerides have 3 esters on them. And if we take triglycerides and we react them with saponification, or we do hydrolysis with base, it goes there and it cuts these esters off. It cuts the ester bonds, right? You get our acids back. We get our long-chain fatty acids, but we get the salts of those. We get the negative charged, right? I was going to say ethanoate ions, but if this was, I don't know what we call it, we just get the salts of the fatty acids instead of getting, this could be stearic acid or something. We'll get sodium stearate, right? Because this will have a negative charge on it. We'll call it stearate instead of stearic acid, like we do here, ethanoate, stearate. Anyways, this is what soap is. Soap are really long fatty acids that are hydrolyzed esters essentially, or the salts of them, and those can react with water and grease really well because they have a really greasy portion, and then they have a portion that contains, positive and negative charges on it, and that likes the water. Anyways, saponification, hydrolyzing esters with base, how you make soap. Okay. As far as amides go, too bad we don't get soap from amides. Amides require actually a more vigorous kind of hydrolysis condition than both the anhydrides or the esters do. And they actually have to have both acid and base, or in acid and base hydrolysis. These are more vigorous sort of reactions. The hydrolysis in hot aqueous acid will give a carboxylic acid and an ammonium ion. You got to remember that whenever we have acid conditions, that our amines get protonated, and they get a positive charge on them, and we call those ammonium ions. In base, right, when we hydrolyze, don't forget, the amide that we're talking about here, comprised of carboxylic acid and amine. So that's why we're talking about it. In acid, you get back your carboxylic acid, okay? But your amine becomes an ammonium ion. In base, you get back your amine just like normal. The amine is a base molecule. It's perfectly happy in base. But in base, we get our carboxylate ion. Because remember, when you have acid, when you have acids, they neutralize in base. So as soon as this thing formed in any kind of way that looked like a carboxylic acid again, the fact that there was base around meant that that hydrogen got scooped up, and really it just looks like that. It's a carboxylate ion. So that's what happens in base, and that's what happens in acid. So shown here is acid. So this is an acid version. So butanamide, we cut it right there. The nitrogen goes one way. We're going to add, remember, we're still adding a water back. So the OH from the water goes back to make the acid, and then the H goes back on the amine. But in acid conditions, there's also an additional H that adds on here because this amine is a base. With sodium hydroxide, just to show you what that reaction looks like, we still get our carboxylic acid in the, oh man, this is an alcohol. So let me fix this. Okay, so here's our amide, and then in sodium hydroxide, we're going to get back this guy. So we get back our amine. Our amine looks just fine, but our carboxylic acid, because of the base present, is going to be in its ion form. So hydrolysis of an amide always gives you an ion, one way or the other. In acid, you get a positive ion. In base, you're going to get a negative ion, and then the molecule switches. All right, reactions with alcohols. Let's look at how anhydrides actually react with alcohols and phenols to give esters and carboxylic acids. We talked about how we could react these with I think I just confused myself what I was trying to say. An anhydride can react with an alcohol and a phenol to actually give an ester and a carboxylic acid. So that's what I want to show. So here we have an acetic anhydride. Remember, this has 2 carboxylic acid pieces on it. So it's going to fall apart, okay? And then we essentially have what we were looking at earlier, the fact that a carboxylic acid and an alcohol can react to form an ester. But then one of these carboxylic acid pieces from the anhydride is still left over, and that's going to just be left over as our acid. So that's all we're saying. That's all I'm saying. That anhydrides will react with an alcohol to result in an ester and your carboxylic acid back. And we actually make aspirin this way. Aspirin is prepared by the reaction of salicylic acid with acetic anhydride. So acetic anhydride is shown here. We want the carboxylic acid portion of this to react with the alcohol portion of the salicylic acid. This is the alcohol portion, the hydroxide, to produce the ester. And so you can see that here. We made the ester from the carboxylic acid and the alcohol. So that was the Ca, and this was the alcohol. And then the leftovers of that is just the leftovers of the acetic anhydride. You could try to make this from just acetic acid and salicylic acid, and the only product would be water in that case. There wouldn't be a leftover acetic acid. But acetic anhydride is actually a much better reaction. You get a better yield. With amines, anhydrides will react with ammonia, which is the simplest nitrogen compound, and with primary and secondary amines to form amides. So ammonia, remember, the hydrogen has to be donated from something. That's why alcohols and amines work, because they have hydrogens to come in and react with that OH that's on the when we were talking about carboxylic acids. But this is the same reaction, There needs to be a hydrogen, though, to leave to form water. So in ammonia, there's plenty of hydrogens. In a primary amine, there's also plenty of hydrogens. In a secondary amine, there's still hydrogens that can do this. But in a tertiary amine, there's no hydrogens. And so tertiary amines can't react. So only ammonia and primary and secondary amines. Primary and secondary. Now, here you see ammonia. Here you see, actually, that's all you see. So there's two different reactions here that you can see what's happening. So if we react 2 moles of amine, actually, you actually have to react 2 moles of amine. One of those moles of amine is required to first split up your anhydride, to react with the anhydride, to form the amide, and to form that other carboxylic acid. The second round of the ammonia is actually required to neutralize that previous carboxylic acid byproduct, turn it into something harmless that isn't going to further react with our, well, also by it being there, it's going to drive, right, if we have lots of this stuff as a product, it's going to drive our reaction backwards. So turning this into that prevents the backwards reaction from happening also. But anhydrides technically need 2 rounds of ammonia or a primary secondary amine in order to react, because there is that byproduct. If we were simply reacting this with a carboxylic acid rather than an anhydride, then we would not need the second round. It would form this and water. It would form the amide and water. So anhydrides are special. What am I showing you here? Esters will react with ammonia and with primary and secondary amines to form amides. So here's an ester. An ester will just basically switch with the nitrogen. Nitrogen is more reactive here. So it takes the place of the alcohol group, essentially, on our ester. And so here it's just displaced the hydrogen. So actually amides can be prepared from carboxylic acids by first converting the carboxylic acid to an ester with Fischer esterification, and then the reaction of the ester with the amine. Amides don't react with ammonia or with amines, so we don't have to worry about further reactions of our amide with any leftover ammonia that's still floating around in there. Remember, this is because amides are kind of hard to make. They're hard to make from carboxylic acids, and so by getting them into esters first, we make it easier. Let's talk about phosphoric anhydrides because of their relevance in biological molecules. So the functional group of a phosphoric anhydride is actually 2 phosphoryl groups. These are the P double bond O groups, bonded to the same oxygen atom. So here, so just so you know, phosphoric acid would be split right here. This is just 2 phosphoric acids, okay, just like an anhydride. We've lost the water here so that the O's could be the same, and these 2 phosphoric acids are connected. So this is a phosphoric anhydride, and this is another phosphoric acid anhydride. This one just has 3 connected, so 3 molecules of phosphoric acid forming 2 of these phosphoester bonds. And just to show you what happens when you put these into water or in our bodies in blood, the pH is a little more than 7, so we end up, it's slightly basic, so it pulls off the hydrogens. So you can see here these charges on the O's, okay? So just to show you what these or phosphoric anhydrides look like. Pyrophosphate is actually a molecule that's an intermediate in glycolysis, or in one of our carbohydrate breakdown cycles. Now, phosphoric acid forms mono, di, and triphosphoric esters. In more complex phosphoric esters, it's actually common to name the organic molecule and then indicate the presence of the phosphoric ester with the word phosphate or the prefix phospho. We're not going to be worrying about naming any of these, but that's how the naming kind of goes. So here's an example. Here's dihydroxyacetone phosphate, or pyridoxal phosphate. Again, shown ionized because this is what they look like in our bodies. Here you can just see how that common name kind of goes. This would be phosphoric acid, but if it's an anhydride, we can call it, in this case it has 2 methyls on it, so dimethyl phosphate. Anyways, we have phosphoester bonds in our backbone of our DNA, as well as in phospholipids, and so they tend to react a lot like the carboxylic acids do. So we can react them with amines, we can react them with alcohols, and they'll form those bonds as well. We tend to like to make polymers. So, step growth polymerization is actually step growth polymers. Polymers, these are formed by reacting two molecules, each of which contains two functional groups. Each new bond is created in a separate step, and I'm going to show you how, I'm going to show you three of the step growth polymers, polyamides, polyesters, and polycarbonates. We looked at polymers already with alkenes. Remember, if you have a C double bond, doesn't matter what we've got on here, okay, we can actually form, the double bonds can just kind of move in between atoms, right? So we get a new bond between these guys. And then, of course, there was a growing chain this way, and then we can add another monomer, and that'll feed in here, right? We would link these together like we did. Now, this only has one functional group in our alkene. So for our polyamides, our polyesters, our polycarbonates, they have to have two functional groups. So let's take a look. So this is a polyamide. Now, I think what I'm showing you here is actually nylon 66. It's called nylon 66 because it comes from two 6-carbon molecules. This is a dioic acid, so it's got two carboxylic acid functional groups, and then 6 carbon. This is a diamine. It's got two amine functional groups. And if you can imagine, staggering these guys so that the amine side reacts with the carboxylic acid side to form an amide bond, and then another amide bond, and then another amide bond. So alternating, right? So if you do this, you get nylon 66. This was the first synthetic polymer, first truly synthetic polymer. And they used it, for lots of different things. It replaced cotton for a long time. And it was really sturdy. Now, a lot of research went into figuring out that if you actually include a benzene type ring inside these amides, that you increase the strength. And so they did that. They stuck in benzene rings within these, and they developed a compound called Kevlar. Kevlar was a lot stronger and a lot lighter than things around the same size. So you can use Kevlar to make ropes and like ties for anchors, and support fibers for your tires. And if you made a Kevlar cord, it's actually 20% the weight of like a steel cord the same size. So just as strong, but much lighter. So Kevlar can actually even be woven into fabrics to make things like raincoats and bulletproof vests and the such. So that comes from a polyamide. Polyesters, these are, you've heard of polyesters before. Polyester, actually on its own, polyester was invented a while back, probably right after they came up with nylon. Polyester is a little stiffer than nylon, so they marketed it as being able to resist wrinkles and that kind of stuff. Ultimately, I think it is a little too stiff, so they have to work it into cotton and do like polyester blends because it's a little too stiff. But polyester here, it's just multiple esters. And remember, esters come from either dioic acids and diols. So two alcohols here bridging what would be the next carboxylic acid, and then the alcohol, and then the next carboxylic acid, and so on, right? Alternating. Mylar, I guess that's the name of, or these are some formula names of these polyesters. Polycarbonates, little lesser known compounds, or at least lesser discussed. We didn't talk about carbonates very much. Carbonates can also be made into these polymers. And Lexan, which is a polycarbonate, is the most familiar one. These things can be made into, trying to think of, like sport equipment, like helmets and other high impact sort of resistant to impact sort of materials. Okay, I'm spacing on unbreakable glass, like that clear plastic that you can, like I want to say fish tanks maybe even are made out of polycarbonate, like the thick see-through plastic that you can't, airplane windows and stuff, polycarbonate. Okay, here you can see Well, this is a real specific compound here. We're reacting phosgene with disodium salt of bisphenol A. Okay, whatever. We didn't go over these reactions, so if this looks like gibberish to you, it looks like gibberish to me too. These are actually held together by forming, I guess we're calling the carbonate, the carbonate bond here when we have the carbonyl carbon reacting with, it looks like it's just an ester, right? Because it's, I mean, this is just an ester bond right here. I wonder why why it's not called a polyester. What's polycarbonate about it? Well, I don't know. I don't know why it's called polycarbonate. Let's do some research. Oh, that was easy. They're esters of carbonic acid. So carbonic acid is this guy. So carbonic acid. I guess this is like diformic acid or something, right? Formic acid is when we just have the H on it. So this is like a dioic acid of like that simplest acid there is. This is actually the H2CO3. If you've ever looked at carbonic acid, if you remember this at all vaguely from your, I don't know, Gen Chem, if you took any Gen Chem, carbonic acid. So what we actually use in our bodies, we have a bicarbonate, which is just the HCO3 buffer system. Anyways, carbonic acid is the starting molecule here, though I don't really see it in there. Do you see carbonic acid anywhere? I guess the fact that it kind of is here. So phosgene is apparently a derivative of carbonic acid. So they're showing us a really weird polycarbonate here. Polycarbonates probably look a lot more normal. This polycarbonate is made with a derivative of carbonic acid called phosgene. So if we wanted to see a real reaction here, we probably would have started with the actual carbonic acid molecule rather than phosgene. But still, that would react with presumably an alcohol, an OH, and we would get polycarbonate esters. Okay, so polycarbonate is just an ester of a particular acid, a carbonic acid. I'm sorry that we had to figure that out together, but I wasn't going to just say, oh, figure out what polycarbonate is. And this picture was not very good. All right, so that's just an overview of those types of bonds, guys. The polymers, again, we're going to look at some phosphoric esters or phosphoric anhydrides as we move forward into the to the biochemistry side of this. But the reactions of the amides and the reactions to form those esters are also important because the amide formation, for example, we see that reaction with amino acids when we form proteins. Amino acids have two functional groups on them. They have a carboxylic acid and an amine. Instead of having dioic acids and diamines, they've got one of each, and so we can just string them together and connect them. Our sugars as well. Our sugars consist of carboxylic acids and alcohols, so they form some esters as well, and we actually will form acetals and hemiacetals when we link monomer sugars together and start looking at sugar polymers in the next chapter, like glucose and amylopectin and not glucose, glycogen and cellulose and those kind of things. So that's the relevance of these reactions, and the relevance of looking at these functional groups is because they are going to show up later on in a more biological context. All right, guys. See you guys in the chapter 20 lecture video. Don't forget to email me with your questions or drop by office hours if you need to. And I'll see you guys then. Take care.